Okay, let's try a few examples to create a root locus for transfer functions. Let's imagine we have a simple system, and the g in this case represents the open loop transfer function. Remember, root locus only makes sense when we're talking about the open loop transfer function, because we're trying to find where the closed loop poles go. So do not try to apply the root locus method to a closed loop transfer function, because it doesn't make any sense then. It's only the open loop transfer function. So in this case, we've got a couple of poles, a pole at -2 and a pole at -3, and we've got a 0 at -1. So the system is already factored, so we can start and plot these. We've got a 0, which we represent as a circle at -1. We've got a pole we represent as an x at -2, and then we've got another pole here at -3. So -1, -2, -3. And so we've got these poles and zeros. Now, one of the first things we want to do is determine how many branches are going to go to infinity. And in this case, or in all cases, we simply subtract the number of poles, or the number of zeros, from the number of poles. So we've got 2 poles minus 1 0, so we've got 1 branch going to infinity. So we know if we've got 1 branch going to infinity, it goes at -180 degrees. And so let's see if that makes sense here by finding out where the root locus lies on the real axis. And we do this by the pin up, pin down rule, as I call it. We're going to start at the origin, have our pin at the origin, pin up, and we're going to move along the negative real axis until we find a pole or a 0, and then we're going to set our pin down, and we're going to draw till we find another pole or a 0, and then we're going to pick it up, and we're going to move it along till we find another pole or 0, and we're going to put it down, and we're going to draw until we find another pole or 0. In this case, there are no other poles and zeros, so this is going to go to infinity, which is exactly right. When we have 1 pole going to infinity, we have, or 1 branch going to infinity, it is at -180 degrees. Now, so this is actually the root locus for this system. It shows all possible solutions as the gain in this case, which isn't represented here but is understood here as a k, as our k goes from 0 to infinity. And so we're going to start at our open loop poles, and we're going to move to our open loop zeros, or infinity. So these branches are going to go from the -2 to -1, and then the other branch is going to go from -3 to infinity. So what is going to be the response of this as we start cranking the gain up? Well, at very low gains, what we're going to have are these 2 poles, the pole at -2 and -3, are going to play together. Okay, they're going to interact, and we're going to get some first order-ish system. Okay, but this 0 adds a little bit of complexity in there because it reshapes the step input as we come into it. But we're going to get something that looks first order-ish. Okay, now as we start increasing the gain, what's going to happen is that our pole that was at -3 is going to start zinging out here towards infinity. Pretty soon it's going to become high frequency, and we've talked about this when we have a pole that is 10 times larger than the dominant poles, it becomes high frequency and we can ignore it. And so our dominant pole is going to be the poles in here that are going to be between -2 and -1. So this response of this system is going to be a first order-ish response. Okay, it's never going to get very oscillatory. It's never going to get very fast because it's stuck here between -2 and 1. And so it's going to be a fairly slow little first order kind of response. Okay?